This time the projector is working, so I'm afraid you're going to have to see some slides. I'm sorry. So, but at the end, I will reveal the winner of the competition. And I've been analyzing the data. Now, the first thing to say is that I'm going to take up till about 12 o'clock. And after that, we'll go to the computer room, and there will be a change in the plan. There'll be, I don't know, but we've decided that for statistics, actually, a better computing environment would be R. Has anyone done any R before? Oh, great, you all got to learn. Lovely. It's a package. It looks quite like the SciPy, but it's got some very, very good graphics features. You can very quickly produce very nice pictures, and also it's got built in all the statistical functions that we will need in the second and third weeks. In particular, when we get up to quite complex regression analysis, looking at what factors influence risks and rates of events. So I'm sorry, no, I'm not apologizing. You are going to have to learn R. Now, apparently in AIMS in Ghana now, they're starting both doing Python and R right from the beginning. R is incredibly useful. It's within the whole statistics world, and that includes bioinformatics and so many areas that use statistics for big data use R. It's what I like using. So it's incredibly useful to know both, essentially. You can call R from Python. There's RPy program, so you can run R from within Python. So that will be an option if you want to do it. Now, fortunately, Emil, there he is the R star, and and he will, before lunch, he will give a tutorial to you and me on some, because he can do some clever things on using R, and I think you'll like it. I think you will. I think it'll make the next 2 weeks be very easy. I think very about the computing. I think you'll like it. So that's what will happen for that. Okay. So in the meantime, we're going to do 3 things this morning. I want to talk about the coin flipping that we did. I want to do quite rapidly some technical things on continuous random variables, but with an emphasis on one particular thing, which is essentially something that's really important, which is to do with calculating tail areas in normal distributions. It's something that comes up again and again and again, that we just need to be able to we need to be very familiar with these ideas. And then I will finish off with the great bean competition and a marvelous prize I have for the winner. Okay, so just to, is that okay? What we'll do today. Right. Oh yeah, R, yes. And there is also an assignment that's on the website that's got a few sort of theoretical questions, which we'd like to do in LaTeX. If you can, it'd be very good to do them in LaTeX, good practice. And then some R exercises, which are not to be assessed or handed in. That's just R exercises to do in R. And the assignment we'd want back on Monday's a holiday. I would say Monday morning. It's a holiday. What should I say? If I say Tuesday, what should I say? Emma? Tuesday? Yeah, okay. Tuesday lunchtime. Tuesday lunchtime for the assignment back. Yeah. Yeah, because it's all got to be sent in to Emma. Fine. Okay. Right. Yes. The coin flips. If if we saw that written on a piece of paper yesterday, do we think that would be real or imaginary? Real. Why do we think it's real? The sequences, because when someone's making something up, they never write tail, tail, tail. I don't think anybody ever does that when they're making one up. But this is really common for this to occur. So one way to distinguish, a formal way, if we want to be, you were just doing it by judgment, but we could do some formal statistics on this by looking at what is the longest sequence of either heads or tail that we could expect. Now, I don't know how to do that exactly, to work out what is the probability in 20 heads and tails of getting a sequence of 4 or more. I wonder, I'm sure you could do it exactly. Somebody clever must be able to do it. You could have to work out all those sequences, all those bits, and there's some overlap. I think it's quite a complicated problem. Very roughly, you could say a sequence of length 4 being all the same has probability, being all the same, yes, is 1/8, because it's 1/16 of getting 4 heads and 1/16 of getting 4 tails, and so it's a 1/8 chance of getting a sequence of any 4 the same. But there's lots of possible sequences of 4. There's 16, in fact, although they overlap, of course. So we might expect roughly 2 runs of 4 in any sequence. That's a very rough calculation. It's probably too much. But I'm going to cheat. I cheat. I mean, I'm not a real mathematician, because faced with a problem like this, I don't go to my pencil and paper. I go to the computer and simulate 10,000 of real flips, real sequences, and just go through the 20 sequences and simulate them, and then count at each simulation, count what is the longest run. The other statistic that people use to check is what's called the number of switches. How many times, so there's a switch there, and there, and there, and there, and there, and there, there, and there. There's that many switches, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which it turns out is exactly how many you would expect. So that's just right. That's just how many switches you would expect from a real... Now why, and when people make up a sequence, they put too many switches in. They put too many 1s and 2s, so there's too many switches. Now the intuition there, 10 switches, have people got a feel of why there might be 10 switches? Can anyone explain why 10 switches sounds reasonable? More formally is this idea that how long you have to wait is a geometric series of 0.5. And we know from our homework that the average length of a geometric series is 1/p. So the average sequence length is 2. So on average, you will throw the average sequence length is actually 2. And so that means there should be about 10 switches. And that's not it goes against people's intuition, but the average sequence length is 2, not 1 point something or other. You know it's not going to go head, tail, head, tail, head, tail. But the average sequence length is 2. So what we do, again, is use simulation. So what I did in R was write a program to do 20 coin flips 10,000 times and just record the longest run in 20 coin flips. So again, I'm embarrassed not to be using maths. I'm just using simulation. But what you find is that the longest run only is 2 out of 10,000. So only in about 20% is the longest run 3. The most common longest run is 4. And 5 is very common, and 6 is very common. Well, about 10% of runs will have 6 in a row, and more than so. That's about 20% will have 6 or more in a row. It's extraordinary. So the point is that when people, when they're making them up, will often just put 2, and you know that that's incredibly rare. So what you were doing, in fact, in your minds was what we're going to be doing next week, which is a hypothesis test. You were saying the reasoning, we're going to be doing this so much, it's exactly the same reasoning used for the Higgs boson. It says, if it was real, let's say you observe this, the longest run was 2. If this was a real sequence, this would be very, very unlikely to have occurred. Because it has occurred, I doubt it's a real sequence and I think it's a fake. So that's the reasoning you're using, and that's the reasoning we're going to come back to again and again and again. That's why the tails of distributions are incredibly important. If you observe something up here, a run of 13, they're almost certainly cheating. Or the coin has got 2 heads, is biased or something like that. So if you observe something up here or down here, it makes you doubt the hypothesis, the idea. Similarly here, for the number of switches, when people make up sequences, they often put in 13 or 14 switches, lots of short runs. And that's very unlikely to occur in a real sequence. So again, if you observe things here, it makes you doubt whether the coin is real. Is that okay? Because that's a really, really basic thing we're going to come back to again and again. And essentially, the Higgs boson, they did exactly the same. They set up a distribution of what they would expect to see if the Higgs boson did not exist. And then they observed something 1, 2, 3, 4, 5. They observed something out there. 5 standard deviations away from the middle. And so they concluded the Higgs boson exists, or something exists, because this would be so unlikely to occur. Now, it's interesting, why do the physicists why do they need something like that? We'll come back to that later in the next couple of weeks. But they observed something out there, 5 standard deviations away. Okay, so we're going to be doing a lot of this, calculating distributions and seeing whether the observation lies in the tail. Okay, now back to the boring stuff. No, it's not boring. It's really, really interesting and important. I'm sorry. Okay, you can look at all these slides yourself, so I'm not going to go through them in every line. Basically, now what we're now talking about is random variables that are continuous. They're not just taking on discrete values, they're continuous. Now, in fact, so they're mathematical. I mean, no random variable is really continuous. When I ask your height, you're going to give it to me just in centimeters or even in millimeters. So it's always whole numbers. But we pretend that it's actually a completely smooth quantity, mathematically. So this is a very mathematical construct. And it means, for example, that for a continuous random variable, the probability it takes on any particular value is 0. There's probability 0 on taking on any value absolutely precisely. The only thing we can talk about is the probability of it lying in a very small area. So when we talk about a normal distribution, we're talking about the probability of it being in a little range, tiny little range. But what is defined, so the probability like that of it equaling something isn't defined. But it has a probability distribution function, the probability of it being less than something. And this is this tail area. So if this is x, this is f of x, and this tail area is incredibly important. And we spend all our time calculating tail areas. Now that means that if we want the probability of lying between 2 points, we just take away the smaller tail area from the bigger tail area. So if I want the probability of it being in here, I calculate, if this was A and this was B, this is f of B is is all of this, that and that. So if I want this area, I calculate f of b and take away f of a to give that bit in the middle. So we do that a lot. The other thing to remember is that the value, if this is, let's say this was 20%, then that is known as the 20th percentile. This point here, where 20% of the area is below it. Now, the most common used one is the 50th percentile, which is the median. It's the value, so I should point to that. It's the value in the middle. So the median is in the middle. The quartiles are where divide the area up into 4. So that, and that are equal sizes, the quartiles. Okay. And if it's, I think all the ones we're going to be looking at, f, this cumulative distribution function is absolutely continuous. It's got a derivative, and that's known as the probability density function. So now we've got a value here, an actual ordinate, f, such that the integral f of x, so this would be, say this area here, capital F would be the integral of this between minus infinity and this point. So we're really just doing standard integration of a curve, back to really basic standard integration. And so it means that the probability of x at any small interval is about f of x dt. It means, for example, that f of x can be greater than 1. We can have these distributions that are greater than 1. You can be greater than 1 in the middle. And that can be really strange. But it's because this height is not the probability of it being there. It's the area. That's the probability, and that's always less than 1. So the actual value can be greater than 1. It's rarely, but it can be greater than 1. It doesn't matter. Okay, so the most common one, as I've drawn up already, is the normal distribution. I won't go through all of that. It's got this formula discovered by Gauss in, well, actually, no, it was really developed by Gauss. It was being used in the 18th century. 1710 or something it was being used. So it's been around for 300 years, and beautiful formula. Draws a lovely curve like that. This is the standard. If you write it in this way, it's got mean mu, variance sigma squared. This is the standard version with value mean 1 and variance 1. That's beautiful. And the tail area of the standardized version is given this function phi. This is related to the error function in physics. Sorry, yes? Sorry? Well, have I got it wrong? Oh, there's a minus there. Yes. Yeah, and there, and there. Yes. Thank you, Alex. Right, I'll put those in the notes. I missed out the minus. You definitely need the minus in there, otherwise the integration will not work. Okay, thank you very much. Now, the important thing is this phi. If I've got a standard normal density like that, with mean 0 and standard deviation 1, phi, and this is often given the value, the z is often given it's often called z. Phi z is that integral like that. And this has got standard deviation 1. What that means roughly is that that's about 1, that's about 2, it's about mine. It means that for a normal distribution, most of the area is within plus or minus 2 standard deviations. That contains 95% of the area. If you go out to 3 standard deviations, that's only about 1 in 1,000. So, and that's best drawn. Here's a nice picture here, taken from Wikipedia or somewhere, stolen from somewhere. that show, as usual, that if you've got a normal distribution with mean mu plus 1 standard deviation, that contains 34% of the area. So the middle bit is 68%. So about 2/3 is between plus or minus 1 standard deviation. Then 95% is between plus or minus 2, and plus or minus 3 contains nearly all of it. 998 over 1,000 of the distribution. Now, the kind of thing we're going to be doing a lot is, do we ask someone, okay, what's the chance of a normal variable lying between 2 points? The trick on all of these things is to convert this to a standard normal so you can use the tables or the computer program for phi. Because this isn't available in closed form. We can't do this integral. That integral cannot be solved in closed form, even when it's right, even with minus. So what we have to do, and it's quite nice, we just take from that one, from all this is still the same identity if we take away mu and divide by sigma. But now this is exactly the same as z. It's a standardized normal, because it's got mean 0 and variance 1. So now we've just got the probability that a standard normal lies between 2 points. A. I got there first.
B.
No, which one should be? That should be A. Yeah, that should be A. Right, second one should be A. Right? Right, so that should be A. So we can just take these values, calculate them, put them into the program, and we get the area within any point. So that's how you would get to these areas if you did that. And we'll be doing this, practicing doing that. Okay, next distribution, the exponential, that's the one that looks like this. It's the classic waiting time. It's the continuous version of the geometric distribution. And we're going to be doing a lot. So it's a lovely distribution, really beautiful. Again, I don't want to go through it in great detail. I wonder what mistakes I've made here. Now, I think this is all right. Oops. It's the standard version has got that density, just e to the minus z, simplest density you can think of. It integrates up to 1. So it's the simplest one you can think of. It just goes like that. That's what it does. Now, and when you've got a parameter in there, it's got lambda e to the minus lambda x. So when x is 0, it's lambda, and then it comes down. And so lambda e to the minus x is the density. This is the distribution function. This is the area less than it. So this is, if that's x, this is f of x, given lambda. And it's got a mean 1 over lambda and variance 1 over lambda squared, which I won't bother to prove because you can do that yourself. Okay. We're going to use this a lot. This is from Wikipedia. Again, very good for distributions. We'll be using this. It's a good waiting time. And it's got this memoryless property. Yeah, it's amazing. With an exponential distribution, here's an exponential distribution. If I'm waiting for something to happen, and it hasn't happened by this time, t, so it's not happened. I'm waiting, and nothing's happened. Then my waiting time from t onwards now is exactly the same distribution. It's got no memory. So it's like flipping a coin. If I'm waiting for, a head, and I flip 2 tails, my waiting time for the head is still exactly the same. It hasn't changed. There's no memory in the system. So it's what's known as the memoryless property. Now, in real life, waiting times often don't have this. For example, human survival is definitely not like this. If I know I've reached 55, I know I haven't got as long to live as someone who's just been born. It is definitely not exponential human survival. Okay, getting on. Now, as you see, I'm going through this quite rapidly because it's better just to read it, I think. Now, the uniform distribution, another useful one. Uniform distribution just says that something could be anywhere between here and is equally likely between A and B. Now, since this area must be 1, it means that this height must be B minus A. Is that right? No, 1 over B minus A. 1 of it, have I got that right? Oh yeah, I got that right there. Yeah, 1 of it, because this is length B minus A, and the product, that makes the area 1. Yeah, goodness me. Right. Whew. So that's got height 1 over B minus A. Distribution function is just the area to the left. It's got this variance, not very intuitive. B minus A, the variance that is B minus A squared over 12. Not very intuitive at all. But that's what it is. Okay. Now, this is a trick. I can't resist doing this because this is a very strange, it's sort of mathematical, but it's a very nice trick. It basically says that for any random variable x, if I consider f of x, in other words, its Taylor, if I sample from some distribution and then measure its tail area on the left, this area has got a uniform distribution. And what it sort of says that if anybody's equally likely to be on the first percentile, the second percentile, the third percentile, the fourth percentile, those are all equally likely. Now, mathematically, it's quite a nice thing to prove. And it's the probability that this is less than some value is the probability that f of x is less than that value. Now I invert this. I take the inverse function. So it's the probability that x is less than f to the minus f. But this is just f itself. So now I've got f and its inverse. They cancel out and I just get f. And that's the definition of a uniform distribution. Now, I went through that very fast, and I think you should look at it again. The crucial thing is why this is important is that it gives you a real neat way of sampling from a distribution. If I want to simulate from a distribution, if I know f in closed form, all I have to do is sample a random number between 0 and 1, and in any computer there's always programs that will generate a random number between 0 and 1, and then take its inverse, and I get a value from that distribution. And here's a lovely example. Let's suppose I want to sample from an exponential distribution. So I want an observation taken from this distribution. Now, how can I take an observation from that distribution? Well, I know that the distribution function is 1 minus e to the minus lambda x. And if I invert that, what do? I put the f over there. And if let me just do that in bits. I've got f equals 1 minus e to the minus lambda x. And so e to the minus lambda x is 1 minus f. So log 1 minus f is minus lambda x. So x is minus log 1 minus f over lambda. Is that right? Is that right? Good. So if I sample a uniform variable and put it in there and calculate this, that will give me an observation from this distribution. Isn't that cool? It's a really neat, and that's used for sampling from distributions. But it's restrictive because you've got to be able to invert f. So you can't use this method for generating from a normal distribution because you can't invert the distribution function in closed form. Okay. Oh no, this is getting really tedious. This is immensely boring. It's so boring, I don't think I even want to go through it. This is just, I'm just going to say these are the things you really need to know. This is just applying the rules of probability to continuous variables. Really boring, and I won't even go through it. That's really dull. This is about independence of continuous random variables. It just means that the joint distribution factorizes. So useful, and we'll come back to that. Oh, this is maybe a bit dull, but incredibly important. If I've got any random variables not necessarily independent, then the expectation of their sum is the sum of the expectations. So they don't have to be any quantities. If I know their expectations, I can just calculate, add those up, and that gives me the expectation of the sum, even if they're not independent. So that's a really important rule. We'll come back to that. Now, variances also add up, but only if they are independent. We did that before with just 2, and we need to bring in covariance if they're not independent. But a lot of our examples, so the variance of the sum is the sum of the variances if independent. Okay, so those are those things. Cracking through, nearly at the beans. Ah, yes. Okay, so how can we use some of those rules? Well, we a binomial can be considered. A binomial, if x is binomial NP, we can think of x. No, let's call that y, as being x1 plus xn, where each xi is a Bernoulli with probability p. So binomial is just how many successes there are, and so we can think of that as if we did the experiments one at a time and just added up the number of successes. Now we know from lecture 2 that the expectation of xi, what's the expectation of xi? P. And the variance of xi, can you remember that? P times 1 minus p, which we just calculated that, because this has just got a, remember it's just got a lump p here and 1 minus p on 1. And then it means that from the previous rule, if we want to know the mean and variance of binomial, we just add these up and we get np and np times 1 minus p, without having to actually work out that directly. Because doing that directly is quite tricky, but we didn't have to do it. Similarly, the sum of n independent Poisson variables is actually Poisson with mean mu1 plus mu_n. Now, I'm not going to, you could prove all these quite easily using the idea of probability generating functions, so a polynomial way of proving it. I'm not going to go through all that. I don't think it's not important for what we want to do. But you can, if anybody is interested, you can prove these things quite easily. Very nicely, nice work. Okay, here's really important things. This is getting now really important for statistics. If we've got normal random variables with mean mu_i and variance sigma I squared, then the sum of these, if they're independent, is normal with mean the sum of mu_i and variance the sum of sigma I squared. So this tells us what happens when we add up normal random quantities. So if they've all got the same distribution, in other words, for all I, these are exactly the same, y, the sum, is normally distributed with mean n mu and variance n sigma squared. Now, and this is the really important thing, x bar, the average of them, that means that is distribution mu sigma squared over n. Now, why is it sigma squared over n? We've got to go back to our old rules. Now, the old rule was that the variance of cy for any c was c squared variance of y. You take the square out of it. And the expectation of cy is what? C times expectation of x. So that means y, if we let c, what do we have to let c equal here? 1 over n. Yeah. If we let c equals 1 over n, then we see that for this one, we have 1 over n squared times variance of y. What's the variance of y? N sigma squared, yeah. And that means we get sigma squared over n. So that, I mean, it's it's not very complicated, but it's incredibly important that when we take averages, the variance goes down as 1 over n. We saw that yesterday with the lottery tickets. You see, when you took the average, the numbers all got closer together. And they go in, and at a predictable rate, they get closer and closer. Oh, yes, this is incredibly dull. And I'm so bored, I'm not even going to go through it. All this says is that the average of random variables tends to the mean. Now, the real mathematicians among you will like all the limit theorems and the deltas and epsilons and things like that, but I'm afraid we're going to skip over them. Basically, it says that if you wait long enough, your x bar will get arbitrarily close to the expectation. That if you're sampling a whole lot of variance, if this is mu, and you're sampling observations from some distribution around mu, when I take that average, it's going to get closer and closer to mu. And the simplest example is if I keep on flipping a coin, then the proportion of times it comes up heads will get closer and closer to half. Get closer and closer and closer and closer to a half. And this was proved in about 1710. Amazing. 300 years it's been proved. Now, this is what we did, I mentioned yesterday. This is the important thing we've been building up to. It really goes beyond that. It says not only is the average tend to mu, it tends to mu as a normal distribution around mu. All these averages end up, when I take the average, it's going to be as if it's drawn from this. And this will get tighter and tighter and tighter. It says that if we take averages of any numbers coming from anywhere, in the end, they're going to look like a normal random distribution around the mean. So basically, what we're saying, and this is an extraordinary result really, is that x bar is normally distributed around mu sigma squared over n, whatever the xi's are. Wherever they come from, they can be uniform, they can be all over the place. If we wait long enough, the average is as if it comes from a normal distribution. Very extraordinary result, really remarkable. And we saw, no, this is the uniform. This shows how it happens. I won't get you to calculate, it's a nice thing to calculate. If you just take one observation from a uniform distribution, it'll look like that. That's the distribution. If you take two observations from a uniform and take their average, it's as if they came from this triangle, this red one. That's the distribution for the average of two uniform variables. 3 is the green one. It's starting to look curved, starting to look familiar. If I take the average of 4 uniform variables, it's now looking like the blue one, and we're almost to a normal distribution. Take 6, it's almost indistinguishable. It's quite incredible. No matter, and that's what we did yesterday with the lottery tickets. I mean, we didn't have too many groups to show it, but really there we were drawing our original numbers from this distribution, but the averages start being drawn from a smaller. Now, in fact, of course, these are also getting tighter and tighter and tighter, but they've deliberately expanded the scale to make them look, so you can compare the shapes. Okay. Oh, right. And that's what we did yesterday. We need to clearly distinguish between sampling an x, a single x, in which case the results will follow the original distribution, and sampling the means, which will follow a normal distribution with standard error, sigma over root n. Now, this is a term, it's an important change in language, that essentially, as sigma is the standard deviation, and sigma over root n is known as the standard error. Easy to make the confusion. This is a property of the original distribution, and this is the property of the mean. Oh yes, yes. And so, for example, this will work with a binomial. If I add up, if I want to look at the proportion of times things happen, it's essentially the sum of a set of Bernoulli variables divided by their count. It's a proportion, the overall proportion of successes. And that's the same as taking a binomial and dividing by the sample size. But we know by the central limit theorem, this will have an approximate normal distribution with mean p and the standard error, which is p times 1 minus p divided by n. Or equivalently, this is an approximation to the normal. You can show this directly if you want, using Stirling's approximation. Okay, nearly at the end of the boring bits. Okay, oh, this was an example. I made this up this morning. Okay, so let's suppose you've got a parliament of size 100. And it's supposed to be based on equal opportunities. But in fact, there's 65 men in the parliament and only 35 women. And somebody says, oh, well, that's just chance. It's just chance. Is it reasonable to think that 65-35 is just chance? And this is the kind of thing that people get asked quite a lot. So is 65 to 35 just chance? Now, I think what this course is about, what I really want the whole course is about, is to be able to take problems like that and turn them into mathematical, a framework. Because the mathematical framework recognizes that this is exactly the same as flipping a coin 100 times and getting 65 heads and asking, does that mean the coin is fake? Or is it, is there something wrong with the coin? If I get 65 heads, is there something wrong with the coin? And we can look at that really quickly, very quickly. It's a pretty trivial calculation. Okay, how do we do it? We recognize, first of all, that we're looking at a binomial distribution. It's a count of the number of successes. So the number of males, if it was equal opportunities, there would be an equal chance of everybody being a male or a female. Every member of parliament. So it'd be equal chance. So the number of males should be a binomial random variable with n equals 100 and p equals 0.5 if equal opportunities existed. We know that that's got mean NP. That's not variance, that's wrong, isn't it? Oh, I see, look, yeah. The variance, what's the formula for the variance? NP times 1 minus p. So n, and this goes around the corner. P times 1 minus p is 100 times, have I got this right? Yeah, the variance is 25, standard deviation of 5. So I now know roughly that the number of men, okay, this is the number of men, and this is if equal opportunities. This should look like, the number of men should look roughly like a normal distribution with standard deviation 5. Now, I remember this goes up, remember that about 95% of the area is plus or minus 2 standard deviations. So what's plus or minus 2 standard deviations? What's the bottom end? 40, yeah. Is that, yeah, 40, because that's 1 standard deviation, 1 sigma, and that's 2. And at the top we got 60. So that's 1 sigma, and that's another one. So 95% of the time, you'd expect it to lie between 40 and 60. 65 is actually 3 standard deviations out. It's what in the Higgs boson language is a 3 sigma observation. For those of you who are following the 5 sigma, the boson, they had a 6 sigma. Were they looking for 5 sigma or 6 sigma? 5 sigma. 5 sigma. They were looking for something up there. Okay, in this case, we're going 3 sigma out. And so what we want is the probability. This is the calculation. You do the x minus mu divided by the square root of the variance, probably z greater than 3. We look that up in our tables. That area turns out to be about 1 in 1,000. So, and we can do this on the back of a net, well, we need a calculator, but this is pretty well, we can do this on a back of an envelope. We can work out, this is not right. This is, well, either a very rare event has happened, it could be chance, pretty unlikely, could be, but I doubt it. And that's where that leaves us. So we're going to be doing a lot of this kind of thing. What's this? Well, this is an example of a hypothesis test. And I suppose what this week has been building up to is trying to get the tools, the probability tools, to be able to do more of this kind of thing, because that's what we're going to be doing next week. Is that okay? It's actually quite an important thing. Is that all right? Can we get on to the beans now? Are there any questions on that? Yeah. Okay. Yeah. No, I mean, this is just the simplest of many methods for generating from distributions. And particularly, this is actually, you can only use this in quite restrictive circumstances when you can invert this. So in many situations, you can't use this. And there are methods like the rejection sampling method. There's all sorts of other ways, for example, to generate standard normal variables. They're all based on generating a uniform number, because that's something that you can always get out of a computer, and transforming it in some way. But often they're based on generating 2 numbers and making some function of the 2 of them to produce the distributions that you want. So these are just built in for what we know as Monte Carlo methods of simulating from different distributions. So I might, if people are interested, I could do a bit more on that, because it's an important topic. How do you sample from different distributions? This is just the simplest And it's actually very restrictive. So it's not, you can only do it in some circumstances. Okay. Are there any more? Yeah.
Maybe can I write something on the board? So
Yeah, sure. You, oh, sorry. Oh, yeah. That's F, yeah. Yep. That's the density, yeah.
this is the exponential.
Yeah.
But you have to say that to reference. Should we go to this one?
Oh, no, that's the little f is interesting. This is the density. Yeah, you need to integrate that, and you get the big F.
So this here, the small f?
Yeah, that's the small f. Yeah.
So I got confused with that.
Yeah, no, exactly. I went over that very fast because it's quite nice. If you have the little f, then the big F is just the integral between minus infinity of x of the little f dt. So that when I integrate that, I just get f is 1 minus e to the minus lambda x. Okay, and similarly, I mean, it's always good to check if we're going to be doing a lot of differentiation. I hope your differentiation and integration is okay, because we're going to be doing a lot of it, a lot. You know, when I differentiate that, I get this function coming out. The lambda comes down, the minus lambda comes down, this disappears, the minus cancels out, and we get this. So we're going to be doing a lot of that sort of routine differentiation and integration. But not too complicated, just standard rules of differentiation and integration. Okay, now, I want to leave time for Emil to get onto his stuff. Now, what we did, beams. Now, this was not just a silly game. This is really important. And it dates back to 1907. And this idea of wisdom of the crowds. It was an experiment done by Francis Galton, who was this very strange Englishman, very eccentric. He discovered fingerprint. He invented use of fingerprints. Seemed to invent weather forecasting. He did everything. And what he did, he was at a fair, country fair, and people had taken an ox, a really huge ox, and it had been butchered, cut up into slabs of meat. So it wasn't just standing there. You know, it had been cut up and laid out on the ground, all these bits of meat. And people had to, it was a competition where you, for sixpence, a small amount of money, you had to guess what it weighed. So you had to guess how much meat was lying in front of you. Great, good competition. And they got 787 entries for this. More than the value of the meat, I think. So it's a good way to make money. And the winner got the ox. You know, you won the ox. The person who got it closest. It's good, a good way to make money, I think. You know, so he got, and he recorded all the values, all the 787. And what he did was plot them out. We could look at this data later. He plotted all this out and found the median was £1,207. That was the middle value. Remember, the median is the middle value, the 50th percentile of the data. And the real answer was, what was it? Oh yeah, £1,198. Incredibly close. So that although people varied from a very wide range of guesses, their average, in the median, was really close to the true answer. And this is known as the wisdom of the crowds. Now, in theory, this means that all of you, if I take the average guess, it's going to be a very good guess. Do you think this is true? So this is a very famous experiment. Okay, so what I did, this was for 50 something, I think it's 54 or something like that. This is the data from yesterday. So these were your guesses. I'm not sure who that was, but never mind. So we thought, whoa, there's thousands of beans in there. Yeah. So you see, yeah, look, the majority are less than 1,000, a lot around 600, 800 and things like that, but quite a few, 1,200s and so. This is just using the simplest hist command in R, and it just does this automatically. You could make these tighter to make a more jaggedy distribution. But that's the hist one. So, what do we think? If we take the mean guess, 977 was the average guess. And the median was 925. So, according to Francis Galton, these should be good estimates for how many beans there are. Even though there's huge spread in opinion, you know, if you are wise as a group, these should be quite good guesses. So, I'm not going to tell you yet what the truth is. Can I? Oh yes, can I show you a little video? I'm going to show you a little video because a friend of mine and I did a similar thing and we did it put it onto YouTube. Here we are. So I'm going to put the sound up. This is me. This is me in my office with my blackboard in my office. Okay, so.
Hello everyone. First of all, let me introduce you to David Spiegelhalter, who we've had on before with our non-transitive dice video, which is one of the prizes on offer in our competition today. But first of all, did you not get the memo? Did you not? We were going to dress up for this?
I've dressed
for the people at home?
This is my mathematical dress.
This is you dressed up, is it? Okay, so David, tell us about the competition we did.
Well, in his last video, James asked you to guess how many jelly beans were in this jar. And he's had over 1,000 entries.
We've had over 1,000 responses. We're going to analyse the results. And we've had a winner, which is in this envelope. Yes, you're right to go, ooh, yes. The winner is in this envelope. The correct answer, I did count all the jelly beans myself, but we will reveal this at the end of the video. So last time I told you about the wisdom of the crowd. So a mathematician called Sir Francis Galton wanted to know if a crowd of people could decide what the correct weight was of a butchered ox. Now, David, what do you think of wisdom of the crowd? Is it real or is it bunk?
Well, it worked in Galton's case because he was at a country fair where people knew quite a lot about meat and about what an animal looked like after being chopped up and laid out and what that actual quantity of meat would come to when they added it all up. But when you're trying to estimate how many beans and something like that, that's quite tricky because you're trying to estimate essentially a volume from just a two-dimensional view of it. People could have some systematic biases. In other words, they could, on average even, guess too high or too low. And I'm going to be really interested to see what the results are.
Yeah, so the wisdom is important.
Exactly.
So unfortunately, we did have to reject some of the outliers, which I just thought were typos, really. And to be fair, Sir Francis Galton had to do this himself when he did it in his original problem. So I felt justified doing that. There were as well some obvious joke answers. If there does turn out to be a Google of jelly beans inside the jar, you'll still win, don't worry, you're still in the competition. Francis Galton actually was charging sixpence, which he thought would be enough to deter joke answers like that. So in future, that's what we'll do. We'll start charging sixpence. We could make 60 quid out of this. But there might as well be some bias, because in this case, people could see other people's answers as well. And we're not sure. Well, but David, take us through what happened. Take us through the data. Let's have a look.
Okay, here is the distribution of the judgments that were made, the guesses that were made. We can see here they range from very low right up to nearly 10,000. Some people thought there were nearly 10,000 jelly beans in that jar. Most of them are around about a bit below between 1,000 and 2,000. And we see a peak here, but a long tail with some people thinking 3,000, 4,000, 5,000 jelly beans in the jar. So we've got a very non-symmetric distribution of judgments here. The problem when we've got a distribution like this, a sort of skew distribution, is that it's not at all clear what measure we should use when we want to say the average opinion. There's a number of different averages we could choose.
Right, so we could use the most common answer, right, which is called the mode average. And in this case, the most common answer was 1,337. Bunch of nerds. What else could we use?
We could use the mean, the arithmetic mean. It means you add up all the guesses that were made and divide by the number of people who entered the competition. And if you do that, you get a considerably higher value, about 2,059 jelly beans. Now the point about the mean is that it's very strongly influenced by these few people who thought there were 8,000 jelly beans in the jar.
So instead we might want to use another type of average called the median average. So if I listed all the guesses in order and I took the middle value, I actually got 1,729. Hey, it's Ramanujan's number. And in this case, the median could be considered the average person's judgment rather than the average judgment. So instead of looking at the data directly, we decided to take a look at the log of the data. So what is a log? The log is the power of 10 needed to make that number. So 1,000 would have a power of 3. It's 3 powers of 10. 10 times 10 times 10 is 1,000. So the log of 1,000 is 3. The log of 10,000 is 4. It's 4 powers of 10. 10 times 10 times 10 times 10 is 10,000. And that's what we did. We took the data and we took the log of the data. And this is what we got.
When you do this, you end up with a really nice symmetric distribution. And in fact, then we can fit a normal curve to that, one of these standard old bell-shaped curves, and it fits the data rather well. And that means if we fit a normal distribution to data, then we know how to take the, looking for the average, we should just take the sample mean of those logarithms of the observations in order to estimate the center of this distribution.
So this is what we did. We took the average of the log of the data and we found that the average power of 10 was 3.23. So we take 10 to the power of 3.23, we get our average now as 1,680. And this is called the geometric mean. It's the mean of the log of the data. And well, what's so good about this?
The geometric mean is a good to use if you think the sort of mistakes people make are proportional mistakes. In other words, they're just as likely to get double the answer as half the answer. And if you think that, and that's what gives rise to shapes like this as a distribution, then you should use the geometric mean. So I think if I really believe there wasn't any systematic bias in people's judgments, I would say 1680 would be our best judgment.
So now let's reveal the answer in this envelope, which David hasn't seen. So David, you're going to be revealing this answer soon. Honourable mentions, I think, to these three people here who actually got the median average of 1,729. So these are average people right here. Another honourable mention to Virtual Noodles, who was closest to our average value of 1,680. He actually got 1,681. But now to reveal the actual answer, which I'll give to David.
Oh, this is so exciting. And the answer is 1616.
1,616, which is actually within about 4% of our average, which is pretty good. And isn't it amazing how it can work like with actual real data? We've actually got a pretty good answer. Congratulations to our winner, DDSS6, who actually got it on the nose, 1,616. And I'll make up a pack for you. It's going to include this top trumps mathematicians and non-transitive dice, whatever I think of. So congratulations again. And if you have been, thanks for watching.
Right. That's amazing. Yeah. It was amazing. Oh God! No, that's enough. That's enough. Shush. We don't want any more. Right. Okay. Now it was amazing that they got it. The geometry is taking the log, and then taking the you take the average of the logs, and then the anti-log of that gave a very good answer for it. So, yeah, it was quite amazing, in fact. And I really didn't know the answer either, so that was quite good. Okay, so the point is that what I did with this was also then, I took the logs, and you do get a sort of slightly more. It's not as nice as the other one, but you get a slightly better. Brings the tail, and you get a more symmetric curve. And this is known when you take a logarithm and you get a normal distribution, the original distribution is known as a log normal distribution. Anyway, Oh yeah, that's it. Okay, so the answer, dum ba dum bum bum pa, da dum da dum da dum. Well, I don't know who did it, of course. Shall we? There were some people. Shall I say how many beans there were? According to the counters, very kind counters there. Say how many there were. 1008. See, 1008, just there. So not bad at all. Your average was only 31 beans out from the average of all your opinions, which is pretty good, I think, as a wisdom of crowds. But nobody said 1008, but somebody said 1002. Was it you? Was that yours? Yeah, this is you. Because I didn't know who it was. Oh, that's fantastic. Well done, Corinne. Hooray. No, it's not a very big prize. Small prize for the winner. Well done. Yeah. Wow, what a star. It's so funny because there were two people who said 1,000, and they're so close. So 1,002, so there we are. Well, it was a great success. So, as a group, as individuals, you may be useless. But as a group, you're fantastic. That's the lesson. Right, okay, I'm going to stop there. And Emil, are you ready? Are you cool to go? If we go upstairs? Yeah, that's great. So thank you very much. And you can ask questions up there. I'm going to come up and learn something as well from Emil.